Trigonometry, Chapter 2, Acute Angles and Right Triangles, Section 4, Solutions and Applications of Right Triangles, Video 4, Angles of Elevation and Depression. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we learned how to solve for all missing parts of a right triangle, given the measures of two sides. It is worth mentioning that this completes all possible solve the triangle scenarios involving right triangles. Because otherwise, we're given a right angle, so we need two other pieces. So it's either two sides, two angles, or one of each. But given two angles along with a third, there's any size triangle with those angles because of similar triangles. So it's either one angle on one side or two sides. Later, we'll explore other types of triangles besides right triangles. In this video, we learn about problems involving an angle of elevation or an angle of depression. We should start by defining both of these terms. An angle of elevation is an acute angle measured above a horizontal line. So think of looking straight forward and elevating your head and having a new line of sight. And similarly, an angle of depression is an acute angle measured below a horizontal line. So again, think of looking forward and tilting your head downward to look at something with a new line of sight. Outside of a coordinate plane, both angles are always positive regardless of direction or rotation. I don't want you to look at this picture on the right and say that's a negative angle because this isn't on a plane and this isn't in standard position. Angles of elevation and depression can be used to solve line of sight problems. For example, a trig student is standing 50 feet from a building. When looking at the top of the building, looking up, his line of sight has a 31-degree angle of elevation. How tall is the building to the nearest foot? Something is missing here. Okay, what is missing here is it's supposed to say that the student is 6 feet tall. So let me pause the recording just for a second. Sorry for that. I proofread this twice before starting the video, and somehow that slipped by. All right, so let's restate the question. A trig student is standing 50 feet from a building. When looking at the top of the building, his line of sight has a 31-degree angle of elevation. If the student is 6 feet tall, how tall is the building to the nearest foot? Well, for any trigonometry problem, especially word problems, you should always sketch a picture that accurately represents a given situation. I'm no artist, but here's my rendition of the situation. We have a building over here and a student standing 50 feet away. The student is 6 feet tall. They are looking at the top of the building. Their line of sight forms a 91-degree angle of elevation with the horizontal. Oh, I also forgot to mention to neglect the distance between the student's eyes and the top of his head. We could take that into consideration, but let's not get too nitpicky in this example. Anyway, observe the triangle formed by the line of sight, the dashed line on the side of the building, this triangle. Now, we can find some of the height using trig because the side of this triangle is not the entire height of the building, but then we could add 6 feet to get the total height. So we'll call the leg of the triangle on the side of the building x, and this makes the height of the building x plus 6. Now, since x is opposite the angle of elevation, and the adjacent side is 50 feet long, it's not labeled, but it's implied because of this little rectangle down here, then we can use tangent to connect the three and say that tangent of 31 degrees is x over 50. As usual, we save any calculations that involve rounding, such as tangent of 31 degrees, until the end. Multiply by 50 to solve for x. Now use a calculator, and we get that x is approximately 30 feet. Recall that the building's height isn't x, but rather x plus 6. Thus, the height of the building to the nearest foot is 36 feet. Let's do a quick angle of depression question. From the top of a 200-foot cliff, a man spots a rock formation 1 mile away. What is the angle of depression for his line of sight? Here's a very crude drawing. Cliff, 200 feet tall, 1 mile away is a rock, looking downward at an angle of theta. Now we're looking for theta, which is not currently in this triangle. However, notice the horizontal line is parallel to the side marked 1 mile, and the hypotenuse is a transversal across these two parallel lines. And by alternate interior angles, we can also place theta down here inside of the triangle. And we have one more problem. The units of measure are not the same, feet versus miles. Easy problem to fix because 1 mile is 5,280 feet. Now we can use tangent because the sides that we have numbered are opposite and adjacent. Tangent of theta is 200 over 5,280. Let's solve using tangent inverse. Remember, no approximations until the end. Theta is tangent inverse of this fraction, and we get an angle of depression of approximately 2.2 degrees. That's what I just said. Now you try. Pause the video and try the following. Find the distance d between the two buildings. Hint, use the bottom triangle. And then find the height of the taller building. Hint, you'll use the upper triangle. And this is similar to the Pearson problem we did a minute ago. We'll have to add the height of the smaller building. Pause the video, give it a try. All right, if you haven't paused the video, here's your fair warning. Solution in 3, 2, and 1. Again, the second problem is similar to the one that we did for the angle of elevation because we found part of the height of the tall building and had to add the height of the small building to get the total height of the larger building.